Good afternoon, everyone, and welcome to the EOL seminar series. It is my great pleasure to introduce our speaker, EOL's very own Dr. Tammy Weckwerth. Dr. Weckwerth is in the remote sensing facility where she is currently the lead scientist for the MicroPulse Differential Absorption Lidar, or MPD for short. Dr. Weckwerth received her PhD at the University of California, Los Angeles, studying boundary layer convection. One of her advisors was Roger Wakimoto, who some of you may know was a former director of NCAR. So it was only natural for Tammy to start her career at NCAR as an ASP postdoc, and she has made a notable name for herself at EOL since then. During her tenure at NCAR, Dr. Weckwerth has worn many hats. She has been the deputy manager for the EOL remote sensing facility. She has been the S-Polka lead scientist. She has been a PI of several NSF field campaigns and remains quite active in the radar and LiDAR meteorology community. So much so that in 2020, Tammy was elected Fellow of the American Meteorological Society. In her seminar, Dr. Weckwerth will talk about water vapor observations from the MPD, which, by the way, received the 2018 UCAR Scientific and Technical Achievement Award. We are using Slido to pose questions, which you can ask at any time during the seminar. The Slido window is located at the bottom of the presentation screen. Please do not be alarmed if you do not see your question, because we are collecting all questions that will be revealed during the Q&A portion of the talk at the end of the presentation. Dr. Tammy Weckwerth, we welcome you, and the virtual stage is yours.
Thank you so much, Jackie, for that wonderful, warm introduction. Thank you to everyone for joining in to listen to the story about the MPD project in EOL. I'm going to tell you about the instrument and how we're using it to better understand the water vapor in the atmosphere. So my role in this project is as a scientific advocate for improved water vapor measurements and as a scientific leader in the effort to use MPD data to understand convection initiation and evolution and boundary layer processes. I'm working on this effort using both observational analyses and data assimilation into numerical weather prediction models. Here I list my collaborators on the MPD project, and they are all essential to every component of my presentation, and they are each so great to work with, so I want to acknowledge their contributions up front. Jun-Kyung Kei is a talented postdoc in EOL, soon to be a project scientist. He is the key creator and the data assimilation expert who has run all of the data assimilation experiments that I'll be showing you. Ya-Chen Fang is an ASP postdoc. She and I are working together on how best to use MPD data better understand moisture variability in the atmosphere and how it impacts convection initiation. Scott Spuler is the lead optical engineer who worked with Montana State University to create this exciting new MPD instrument. Glenn Romine and Jenny Sun are patient advisors and collaborators as we try to get our MPD data ready for data assimilation and to design the DA experiments and then to evaluate the MPD observation impact. Michael Ying did some of our first real data assimilation experiments when he was here on an ASP postdoc. Matt Heyman is an optical engineer and a mathematician who's working to improve the MPD signal processing and is constantly improving the data quality from MPD. Robert Stillwell is the MPD software engineer who's working on all components of MPD, including hardware, and he is the key in the effort to add temperature profiling capability to MPD. Ulrika Ramachka is the data manager in our group, and she does so much more than make sure our data are available to the world. Additionally, she evaluates data quality and contributes to scientific analysis. I really enjoy working with these colleagues, and I very much appreciate everyone's efforts on this MPD project. So here's the outline of the presentation that I'll be giving, starting with some background, including some motivation for water vapor measurements and data assimilation activities. Then I'll describe the MPD instrument and show you some observations that were obtained from MPD. And then I'll spend the bulk of the time to talk about MPD data assimilation using both real data in the OSE and simulated data in the OSSE. I'll end with summary and ongoing work. So there have been several National Research Council and National Academy reports that have highlighted the need for improved thermodynamic observations. One key report was led by Rick Carbone in 2009. It called for a nationwide network of networks in which high-resolution moisture profiles were identified as a high-priority infrastructure need. The next year, When Weather Matters noted that height-resolved boundary layer profiling for severe weather forecasting and accurate quantitative precipitation forecasting is necessary. And more recently, a Basque report on the future of atmospheric boundary layer observations, understanding, and modeling from the National Academies of Sciences, Engineering, and Medicine noted that the future must include remotely sensed boundary layer measurements of water vapor and temperature. So personally, I've been interested in water vapor and its variability since my PhD research. So this figure illustrates the variability of boundary layer moisture during the occurrence of horizontal convective rolls. Rolls are counter-rotating horizontal vortices that commonly occur in the convective boundary layer. They can produce cloud streets atop their updraft branches, and those cloud streets can extend for hundreds of kilometers. For this study, during the Cape Field Campaign in Florida, we launched a radiosonde into a roll updraft branch, shown schematically here. We know that it penetrated an updraft branch because it ascended rapidly through the boundary layer, shown by the ascent rate profile here on the left. Additionally, it penetrated a cloud at about 2 kilometers. So we waited 18 minutes from that same site. We waited for the cloud street to pass overhead, and then we launched another radiosonde outside of the roll updraft branch. Comparing the temperature and the wind profiles between these two radiosonde launches shows very little difference. However, look at the difference in the boundary layer moisture profiles. In the roll updraft branch, the roll circulation tends to mix upward the moist air from near the surface and cause a well-mixed boundary layer. Outside of the roll updraft branch, dry air from the free troposphere gets mixed down into the boundary layer and causes drying. So we can see differences up to 1.5 grams per kilogram in mixing ratio between roll updrafts and downdrafts. Since clouds and potentially storms form atop those rolled updraft branches, this brings into question the representativeness of radiosondes. That is, whether they can really be used to represent the actual atmospheric stability if they are not launched in boundary layer updraft zones. So here's a recent study that uses composites of environmental soundings to understand the thermodynamic impact on deep moist convection. They used Relámpago soundings in Argentina from 44 days when deep convection was forecast to occur. And they composited those soundings into these different categories. 13 convection initiation cases that led to sustained convection are shown on the top in green. There were 19 cases when convection was initiated, but it was weak and short-lived. Those are shown here in blue. And then there were 12 cases that they composited where convection was forecast to occur, but it did not. Those are null cases. So Nelson et al. Looked at 70 thermodynamic and kinematic variables to identify differences between these cases, some of which are shown here, including Brent Bisello frequency, lapse rate tendency, vertical wind shear, dew point depression, mixing ratio, and radiosonde-derived vertical motion. The mean and standard deviation for each of the categories are shown by the solid lines and corresponding shading, with green for CI cases, blue for weak cases, and red for the null cases. So one of the primary differences between the convective cases and the null cases is the water vapor profile, and that's shown most clearly when you look at dew point depression right here at mid-levels. This indicates a dry layer at mid-levels, which can lead to destructive entrainment effects and therefore negatively impact the convective development. So there's been a great deal of modeling work that has allowed for this MPD data assimilation study to occur. So I'm going to list some of the key advances here. The work by Wiseman et al., 2008, showed that high-resolution convection resolving models provide improved forecasting capabilities over parameterized convection models. Snyder and Zhang in 2003 showed that regional ensemble Kalman filter techniques with radar data assimilation greatly improved short-term thunderstorm forecast skill. And Schwartz et al., 2014, showed the importance of optimizing those ENKF analyses to produce better forecasts. There was an early airborne water vapor dial data assimilation experiment by Wolfmeyer et al. In 2006, and they were able to show improved QPF skill in an IHOP case study with that airborne water vapor dial information. So these high-resolution data assimilation experiments require advanced verification techniques to be able to assess the model forecast. Some of the techniques relevant to this study that I'll be talking about include mode for object-based diagnostic and neighbor techniques as described in papers by Ebert, Clark et al., and Schwartz. So Caniglio et al. Studied the value using thermodynamic and kinematic profiles from clamps, examples of which are shown here. So one of the instruments on clamps, which is a mobile platform, is an ARRI. ARRI is a passive remote sensing system that retrieves profiles of temperature and water vapor mixing ratio. Clamps also has a Doppler Lidar that provides profiles of wind speed and direction. So they did this study in May 2016 and May 2017. They only had one clamp system available, so they used real-time sensitivity analysis fields to position clamps where thermodynamic and wind profiles would most likely influence the short-term forecast of convection initiation and growth. The summary of the 12 days forecasts are shown here. So these are plots of FSS, or fraction skill score, versus forecast hour, up to 6 hours. The color shading indicates the forecast quality, with red shading showing the forecast lead times where the ARRI and Doppler Lidar data assimilation improved the forecast over the conventional DA forecast. And the blue shaded times are when the forecast was degraded by ARRI and Doppler Lidar data assimilation. There's more red than blue, indicating that there are more times when the data assimilation of these thermodynamic and kinematic profiles improved the results rather than degraded the results in the 6 hour forecast period. This recent study from DeGilia et al. Looked at a variety of research instruments from the Pecan field campaign from one day in 2015. These panels show comparisons between 2 to 6 hour forecasts from the real-time HER on the top, radar and conventional data assimilation experiments in the center, and then Pecan data that included ARRI, Doppler Lidars, wind profilers, radiosondes, and mobile surface stations. The neighborhood probability and neighborhood ensemble probability forecasts are shown in color, and the black contours here indicate the reflectivity greater than 30 dBz as the verification field. So the best forecasts are when the color fills the black contours. The top panel shows that the real-time HER did not forecast the nocturnal convection initiation within the circled red region. Adding in radar and conventional observations in the center panel did not improve the forecast of that nocturnal CI event either. However, the Pecan data assimilation experiment nailed it and captured both the southern and northern nocturnal CI events. They did a series of data denial experiments to identify which data sets were most important for which aspects of the forecast. They showed that kinematic information from the wind profilers and thermodynamics from radiosondes improved the forecast of moisture advection. The ARRI thermodynamic profiler information increased the mid-level moisture and improved the ensemble probability forecast of nocturnal CI. And then the wind profilers, ARRI, and soundings combined to improve the forecast of upscale growth. So this background shows us that there's extensive motivation for obtaining improved water vapor observations, and that thermodynamic profiling data assimilation shows promise in convective weather forecasting skills. So next I want to talk about the MPD instrument itself. So MPD was possible through a very productive collaboration with Professor Kevin Rapasky at Montana State University. Kevin and Amin Narir, his graduate student at the time, attended the Thermodynamic Profiling Technologies workshop at NCAR in 2011, hosted by Rit Carbone. That introduced us to this exciting new instrument that they were developing in their lab. And after that workshop, we visited them at Montana State University and started a really good collaboration. So let me describe MPD, and it's an embedded acronym. MP stands for MicroPulse, which is a class of laser remote sensors that use low energy or micropulses of light at high repetition rates and use photon counting detectors. D is for dial or differential absorption LiDAR, which I'll describe on the next slide. It's a class of laser remote sensor that measures the difference in absorption from two nearby frequencies. And LiDAR is light detection and ranging, which is a type of active remote sensing that is similar to radar, but instead of sending out radio waves, it uses light in the form of a pulsed laser to measure the ranges. For MPD, we use two tunable wavelengths in the near IR. One, the online wavelength, is near the peak of a water vapor absorption band. Another wavelength, called offline, is off the peak of the water vapor absorption band. It's not attenuated by water vapor. So we look at the ratio of the return signals from the offline and online to get the range resolved water vapor number density, or absolute humidity in the profile. This is shown by the equation on the bottom, looking at the ratio of the number of photons from the online and offline signals. The advantages of this technique are that it's a direct measurement and it does not require external calibration for the narrow bandwidth frequencies that we're using, and it gives very high accuracy. The challenges are that it requires high spectral purity and fidelity. That is, it requires precise tunability and high stability of the laser transmitter. But this has been achieved with low cost, high safety, and low maintenance using commercial off-the-shelf parts. Here's an example of MPD data from two field campaigns in Kansas on the top and Argentina on the bottom. The top panel for each campaign shows relative backscatter up to 12 kilometers, and the second panel shows absolute humidity up to 6 kilometers. We can obtain water vapor measurements from about 300 meters above ground up to 3 to 5 kilometers, or cloud-based. You can see some clouds in the relative backscatter field. They're bright red, and above which we don't have any signal. So we don't, MPD does not see through optically thick clouds. One of the first exciting points that these figures show is that these data are nearly continuous. So the engineers and technicians set up the MPD and tune it, and it just runs continuously for weeks. We can see variability in water vapor amounts and depth. In Pecan especially, you can see variation in the depth of the moisture that is retrieved by MPD. And this is because we don't see as high with MPD during the day due to the strong solar background radiation. But this is super exciting to have these continuous water vapor profiles. We have validated MPD using more mature water vapor sensors, including the passive remote sensors of ARRI and microwave profiling radiometers. This comparison of co-located data sets on a full day during Pecan shows comparable water vapor amounts and depth throughout the whole 24-hour time period. However, when you look at the nighttime period from about 5 to 14 UTC, you can see that the active remote sensing capability of MPD is the only one that allows for detailed information about elevated moist and dry layers, which are not retrieved by the passive remote sensors due to their limited degrees of freedom. And here we compare MPD with co-located radiosondes in red, and ARRI in blue, and profiling radiometer in green. And they all show very high correlations for both the Frappe field campaign on the left and Pecan field campaign on the right. So after MPD was successfully proven, Kevin Rapasky and Scott Spuler received an NSF MRI grant to produce a total of 5 MPDs. These were operated side by side 4 days in April 2019. The profiles look very similarly dry at Foothills Lab. These systems all measure water vapor, but 2 of them additionally measure calibrated backscatter LIDAR through the HSRL technique. And MPD 5 additionally has a prototype temperature profiling capability. So if we look at comparisons of unit-to-unit relative backscatter shown down here in the orange comparison, we see substantial variations from the one-to-one line. These relative backscatter differences are due to differences in the transmitter and receiver efficiencies. However, look at the water vapor comparisons in blue. They nearly exactly follow the one-to-one line. I really like this plot because it very clearly shows the powerful capability of the dial technique, because even though there are differences in the internal components of the different MPDs, the fact that the water vapor is determined by a ratio between the online and offline signals that travel through the same internal components leads to the excellent water vapor accuracy. So the MPD is an excellent tool for obtaining continuous, unattended, accurate water vapor profiles. And next, I'm going to show you about some MPD observations that we have collected. Here's the early composite absolute humidity data of 52 days from the Pecan Field Campaign in Kansas, from 400 meters up to 6 kilometers. We can see the diurnal evolution of the convective boundary layer and evidence of the residual layer. So starting at 0Z, which is 7 p.m. local time, there's a decrease in the depth of the moist air until it reaches its minimum depth at about 12 UTC. Then the moist air deepens during the daytime during the development of the convective boundary layer after 15 Z. We can see a suggestion of the residual layer depicted by this gradient up here at 2.5 kilometers. Around 19 Z in the early afternoon, there's a peak in the moist layer at an elevated peak in the water vapor content around 4 to 5 kilometers. So we wanted to see the characteristics of the water vapor profiles on days with convection. So we used radar data to separate the days into convective and clear days. And here are the composite time series for those classifications. With the clear days on the left, the convective days composites are on the right. So compared to the clear days, the convective days tend to have more low-level moisture for the entire period. There's more mid-level moisture in the early afternoons and less diurnal evolution in the depth of the moist air on the convective days. So it's so exciting to see these continuous water vapor profiles, and we continue to investigate the range of potential applications. And these early MPD measurements made us want to see more. So after those 5 MPDs were completed through the NSF MRI grants to Rapasky and Spuler, we took them into the field for a network demonstration project the summer of 2019 and co-located them with ARM facilities in northern Oklahoma at the ARM SGP site. The 5 MPDs were positioned within these red circles and were separated by about 30 to 50 kilometers. And they were co-located with ARES and Doppler LIDARs. And at the central facility here, there was also a Raman LIDAR, and ARM launched 3 hourly radiosondes for the entire 3-month period in support of this demonstration project. The primary objective for our MPD network demonstration field campaign was to do engineering tests of the network of MPDs, but we are also investigating some science questions. For example, what is the water vapor variability across the network? How does it impact convection initiation and evolution of storms? So here we show 2 days, the 14th of June, which is a day with nocturnal convection initiation that we will use for the data assimilation study that I'll talk about next. And we compare that convective day with the clear air day on the 13th of May, when there were no radar echoes near the SGP site, whose location is shown by the 5 red dots. So here's the time series of the 3 hourly radiosondes, relative humidity, and wind profiles for the 24-hour periods. The radiosonde data show stronger southerly winds on the convective day and higher relative humidity amounts throughout the day. These black vertical lines indicate the time of the corresponding radar image. At 5:25 UTC, which was the time of nocturnal convection initiation, note the elevated moist layer at about 3 kilometers. So now we can look at the diurnal variability of absolute humidity profiles from each of the 5 MPDs to see how they differ between the convective day and the clear air day. Here we're showing the 24-hour mean absolute humidity in black, with 1 standard deviation from the mean shaded gray. The minimum values observed throughout that day are in red, and the maximum values of the profiles of absolute humidity observed are in blue. The convective day shows greater moisture compared to the clear air day, and much greater temporal variability throughout the day, as shown by the larger amounts of gray shading. Additionally, there is more spatial variability amongst the 5 MPDs on the convective day, the 14th of June. The spatial variability between the different MPDs is more clearly shown with this depiction. Here we're showing the mean 3 hourly profiles from each of these 5 MPDs, with each MPD now shown by a different color. As we showed before, the convective day has more spatial moisture variability, especially in the 0 to 6 UTC nighttime period, while the clear air day shows that the mean profiles are more consistent with each other across the network. For the 14th of June, MPD 1 and MPD 3, shown in the green and the black profiles, which are located in the western part of the network, illustrate that there's moisture variability across that network. They both show extended periods of elevated moisture from about 1 to 2.5 kilometers above ground level. This was such an interesting feature that illustrated variability across the network and could potentially be important for elevated convection initiation. So this led us to choose the 14th of June for our first data assimilation experiment. So these MPD observations can be used for boundary layer evolution studies and pre-convective studies. And we're also going to talk about how they can be used for data assimilation using 2 different techniques. So these different types of techniques are shown schematically here with these flow charts. So simultaneously, we're doing OSE studies, which are observing system experiments done with real data, and OSSE studies, which are observing system simulation experiments that are performed with simulated or synthetic data. For the OSE, or real data experiments, we use real observations, such as A and B. Then, for example, we can investigate the observation impact on the forecast skill of observation A alone and compare that with the impact of assimilating observation A and B combined. So we're doing these OSE studies using the MPD Network Demonstration Project data from the ARM SGP site. The OSSE framework on the right allows us to investigate the observation impact of existing instruments through the simulation of those data sets and compare it with the potential of new data sets via simulated data from those potential future instruments. So within the OSSE, we can again compare the observation impact, this time from simulated data from potential existing observations A and B, and compare that with the added value from simulated data from future potential observational data set C. So I'm going to first show you MPD experiments from the OSE, or real data assimilation experiments. We're using the 14th of June, which is the convective day of the MPD Network Demonstration Project that I just showed you. This radar reflectivity time series shows nocturnal convection initiation occurring at 5:25 UTC, which is 025 this past midnight local time in north central Oklahoma. The convection initiates near the MPD network and organizes into a linear structure that extends southward into southern Oklahoma and northward into central Kansas, and then propagates eastward out of the network. This slide describes our experimental design for the OSE study. We're using warp dart with a 15-kilometer outer domain and a 3-kilometer inner domain with 43 vertical levels. We use 60 ensemble members generated with random perturbations at 0Z on the 14th of June and run 12-hour forecasts, and this is our no DA experiment. For MPD data assimilation, we start with the 60 ensemble member forecast at 3 hours here, and then we assimilate MPD data every 15 minutes for 5 hours, and then produce these 4-hour forecasts for the MPD DA experiment. Additionally, we take the ensemble mean analysis field and run no DA and MPD DA deterministic forecasts for further comparisons. So here are the MPD data that we're using for this real data assimilation experiment. The data assimilation window is 3 to 8 UTC every 15 minutes and is shown beneath each panel. On this day, as I showed earlier, the MPDs in the west show more elevated moisture. Additionally, there's just higher moisture to the west and deeper moisture in the west compared to the eastern MPDs. So here are the results of running deterministic forecasts, starting from the ensemble mean of the analysis, comparing the top panel showing the observed hourly radar reflectivity fields with the no DA experiment in the middle and the MPD data assimilation experiment on the bottom. So both DA experiments forecast a linear pattern of convection. However, the MPD data assimilation experiment helps to improve the timing, structure, and location of the reflectivity forecasts near and downstream of the MPD locations. This is especially true at 9 and 10 UTC, which are the shorter forecast time periods. And here are the comparisons of those 60 ensemble forecasts from the no DA and MPDA experiments. Within the red dashed triangle up here, we calculate the accumulated precipitation amounts and plot the time series. So the black blocky line shows the stage 4 hourly precipitation time series. So that is our observed truth. The blue lines show the precipitation generated by each of the 60 no DA members, and the dark blue line shows the ensemble mean. The yellow lines show the precipitation generated by each of the MPD DA members, and the red line shows that ensemble mean. We can see that MPD data assimilation reduces the uncertainty of the precipitation forecast at the early lead times. The MPD data assimilation experiments forecast later precipitation onset and greater precipitation amounts and are more consistent with observations compared to the no DA ensemble forecast members and mean. A modeled precipitation distribution within that red dashed rectangle at 8 UTC is shown right here. The ensemble members without DA forecast lower precipitation amounts compared to the observed precipitation, which is shown by this line. Many of the ensemble members with MPD DA forecast too much precipitation, but it's more consistent with the observed precipitation amount. So we're encouraged by the positive impact of the MPD data assimilation, but we hope to further improve the forecast skill by assimilating co-located ARRI and Doppler Lidar data to additionally include the temperature and the wind profiles. So the OSE, the real data assimilation study, suggests that there's a positive observation impact of assimilating MPD data. And next, I want to talk about the OSSE study. For our OSSE study, using simulated data, we chose a pecan case study on the 15th of July, which consisted of convection initiation in eastern Colorado that merged and formed a nocturnal MCS in western Kansas. That MCS produced multiple outflow boundaries and bores as it interacted with the low-level jet and grew upscale and propagated northeastward. This case was documented in a comprehensive observational analysis by Grafnick et al. In 2018. And here's the experimental design for our OSSE study. Again, we are using warp dart with a 15-kilometer grid spacing in the outer domain and 3-kilometer grid spacing in the inner domain, D2. Here we have 70 vertical levels. This map shows the locations of the data sets that we will simulate, including conventional surface stations in the blue dots and sounding locations shown by the red dots. And we're going to co-locate the MPD locations with the 45 National Weather Service radiosound sites across the US. So the first step of doing an OSSE is to define the nature run, or the truth, within the OSSE framework. We do that by running WARs with 40 ensemble forecast members that were created with initial random perturbations. We look at each of these 40 members illustrated in these thumbnails and identify the best member that we call the nature run, and that is our truth. We identify the worst member, which we'll use as a reference field, and try to improve upon that via data assimilation, using data simulated from the nature run. We use a combination of objective analysis and subjective evaluations of the intensity, shape, location, and evolution of convection to identify the members to use as the nature run and control run. We selected the member outlined in blue as the nature run and the member outlined in red as the control run. And here are the 1 to 7 hour forecast reflectivity comparisons between the nature run and control run, with the observations of reflectivity shown on top. The nature run compares very well with the observed reflectivity structure, orientation, timing, and evolution. The control run does not produce an MCS. In fact, it hardly produces any convection at all. So I'd like to describe our different OSSE data assimilation experiments here. This plot shows the locations of the 11 National Weather Service sounding sites in the inner domain. And for this OSSE, we co-located those MPDs with the sounding sites. Remember now, in this OSSE, we're looking at only simulated data. We're not using any real observations other than what I just showed you of using the radar reflectivity field to choose the nature run and the control run. So now the nature run is our truth. In our data assimilation experiments, we first assimilate 12 hours of simulated conventional sounding and surface station observations with 3-hour cycling. Then at 0Z on the 15th of July, we start our different ensemble DA experiments with 15-minute cycling for 3 hours. So this shows us the number of observations assimilated during the 0 to 3 UTC DA window in the lower right here. To create our simulated data set, we matched the actual sounding and surface station data timing and locations that were available for assimilation on the 15th of July, 2015. There were sounding observations only at 0Z in this time window, but there were multiple surface station data sets with 15-minute cycling that we were able to use throughout this assimilation window. And additionally, we created MPD profiles from each of the 45 National Weather Service sounding sites every 15 minutes. At our final DA cycle time of 3Z, we take the ensemble mean to use as initial conditions, and we run the 9-hour deterministic forecast for each of the DA experiments that are shown here. So we have the control run, which I've described. There's no data assimilation within it at all, and we've seen this produces a poor forecast. And we compare that control run with surface station data assimilation alone. And we call that SFC. The next experiment adds in the sounding wind, temperature, and pressure to the surface stations. Note that this experiment has no moisture profile information. The next experiment that we call SFC plus SUT please plus SQ adds in the water vapor profiles from the radiosondes. So this experiment includes both surface stations and soundings. And looking at the time series of available data, we see that we have sounding information only at one time, only at 0Z, and then no sounding information will be assimilated for the next 3 hours because there were no soundings available in this time period in reality. For our MPD DA experiment on the bottom, we include the simulated surface stations, the simulated sounding, wind, temperature, and pressure, and the MPD moisture. And we have those MPD moisture profiles available to assimilate every 15 minutes. So here are thumbnail comparisons of reflectivity for different forecast lead times. We're comparing the different data assimilation experiments with the top row, which is the nature run, which is the truth. The surface station only experiment in row 3 is improved over the control run, shown in row 2, and produces some convection. The addition of the sounding profiles in both rows 4 and 5 does not add very much beyond the surface stations alone, maybe increases the intensity of convection. But the addition of the simulated MPD data in the bottom row produces the best qualitative results in reproducing the nature run's timing, structure, strength, and coverage of the NCS. And this is consistent with the quantitative metric of fraction skill score shown here. The FSS is calculated within the inner domain. The higher the FSS, the better the forecast. We can see that the MPD data assimilation, shown by the magenta line, produces the best precipitation forecast results over nearly all thresholds of rain rates, radii of influence, and forecast lead times. And next, we're going to investigate why the MPD data assimilation improves the forecast skill. First, we're going to look at the integrated precipitable water within the inner domain and the 850 hectopascal wind field at the final DA time. If we look at the region within that orange ellipse, north of the frontal boundary in the nature run, we can see that the wind field is not represented at all by the control run. Assimilation of the surface station improves those low-level winds in the orange ellipse and shows an easterly component in contrast to the control run. And all of the other DA experiments also show the similar wind fields due to the addition of the surface station data. The maximum in the precipitable water vapor field and the structure of it is best represented by the additional information provided by the assimilation of the continuous MPD water vapor profiles. Now we're going to look at how this moisture is distributed within this vertical cross-section across the convection from A to B. The top left panel shows the nature run water vapor mixing ratio profile up to 4 kilometers. Note the elevated moisture that occurs around 2 kilometers in advance of the convection in the nature run. The other panels show the difference fields compared with the nature run. So darker colors show larger differences and less accuracy. When it's blue, that's indicating a dry bias. And we can see that there's a dry bias at this region of elevated moisture in advance of the convection for all of the experiments except for the MPD experiment, which really minimizes that dry bias. So the gray triangle at the bottom of the MPD experiment panel right here is the longitude of Dodge City, which is the location of the nearest MPD to this cross-section. And we're seeing that the best water vapor mixing ratio analysis in the pre-convective region is obtained through assimilating the MPD profiles. And this result extends to the forecast times as well, as the moisture field is improved by the 15-minute DA cycling of those MPD profiles. Looking further at the profiles in the region in front of the NCS, we can look at these fields. So the mean within box A in advance of the NCS are shown here for water vapor mixing ratio, temperature, dew point temperature, divergence, CAPE, and SIN. The truth, or the nature run, is shown in red, and the MPD data assimilation experiments is in magenta. So the divergence, the temperature, and SIN profiles are all similar for all DA experiments and are improved over the gray control run. The water vapor mixing ratio, dew point temperature, and CAPE which are all the variables that are impacted by water vapor, are most improved with the MPD data assimilation. And this is especially true from 1.5 to 3 kilometers MSL. So for this case, data assimilation of MPD's continuous water vapor profiles are critical to improving the moisture profiles, especially at mid-levels, in advance of the convection. And this in turn helps to improve the forecast of the evolution of convection in this region. So since we're seeing positive observation impact of assimilating MPD data on convective weather forecast skill, we wanted to investigate what would be the optimal spacing of a potential future network of MPDs. This follows the nationwide network of networks concept. So the MPD we already ran is in the upper left. And that uses MPDs co-located with the 45 National Weather Service sounding sites. They have a nominal spacing of about 300 kilometers. And we compared that with these different spacings and put the MPD sites at random locations given these different spacings, ranging from 229 MPDs with 130 kilometer spacing to 33 MPDs with 380 kilometer spacing between them. So we compare the results for this 15 June case study using the FSS. The original OSSE is shown in black. I realize there's lots of colored lines on top of each other, so let me separate them out a bit for you. So the MPD spacing of 200 to 270 kilometers, shown by the red and blue lines, seems to be optimal for this case and will require on the order of 58 to 74 MPDs across the US. The MPD spacing of 130 to 150 kilometers does not seem to be necessary. This would require about 200 MPDs and may cause an imbalance of the mass in the wind fields in the data assimilation experiments. Additionally, it may cause problems due to correlations of closely spaced MPD profiles. The MPD spacing of 320, 380 kilometers, shown in green, has little impact on the precipitation forecast for this day, as the MPDs are just too far apart. We expect this result to be case and scale dependent, and we'll run experiments also with other cases. So the MPD data assimilation experiment within the OSSE has a positive observation impact for this case study during pecan of nocturnal convection initiation. So to summarize, MPD is a new tool to accurately measure continuous profiles of water vapor. MPD data assimilation suggests improved forecast skill using these continuous MPD water vapor profiles. Our short-term OSSE forecasts of convection initiation, evolution, and precipitation of the MCS that occurred during pecan on the 15th of July are improved by assimilating MPD profiling data in contrast to assimilating conventional surface and radiosonde observations. And this improvement of convective intensity and evolution of the forecast is attributed to the correction of elevated moist air ahead of the MCS, which is possible due to the frequent updates of the high-resolution MPD water vapor profiling data. So our ongoing work is a lot. This includes engineering improvements. The engineer and technician teams of MPD are adding calibrated backscatter and temperature profiling capabilities and testing these prototypes with 2 MPDs. They're reducing the minimum height to 225 meters above ground. And through a collaboration between Matt Heyman and Willem Marai at University of Wisconsin-Madison, they're investigating the use of Poisson total variance, a sophisticated processing technique to extend the maximum height to 8 kilometers. We're working to assess the horizontal and vertical moisture variability with data from that MPD network demonstration project to study boundary layer evolution and convection initiation and upscale growth. We're using a NOAA grant to determine the optimal combination of thermodynamic and wind profilers for improved convective weather forecast skill. And we realized that we can likely improve upon these results with the addition of other instruments. So we intend to add other EOL instruments into the OSSE study, starting with those that are proposed for LOTUS, or Lower-tropospheric Observing System, which is a plan for a suite of ground-based profilers and surface stations to be used for planetary boundary layer observational studies. So I'd like to end with some grateful acknowledgements. First of all, to NCAR and EOL for supporting this research over the years. Also to NOAA for supporting a new research grant to Glenn Romine, Dave Turner, and I to investigate data assimilation using the MPD, ARRI, and Doppler Lidar. And to the ARM program for graciously supporting our MPD network demonstration project and for providing all of the complementary instrumentation, particularly the 3-hourly radiothon launches for 3 months. And now I thank all of you out there for listening, and I'd be happy to answer any questions you may have.
Great. Thank you, Tammy, for a wonderful presentation on water vapor and weather forecasting as seen through the lens of MPD and the data assimilation of MPD. So we have plenty of time for questions. Our first question is from Jørgen Jensen. Absolutely great presentation. For the development of the strong convection, is the importance of the mid-level moisture mainly due to 1, serve as the main inflow air, or 2, to lead to lessened evaporation following entrainment of moist versus dry air?
Thanks, Jan. That's an excellent question. I think that both are true. So my own personal view is that I think number 1 is most critical in these cases that I have chosen to present, because these are elevated convection initiation cases where the inflow to the storms is obtained from aloft. It's obtained from above the surface layer. So I think that the mid-level moisture in an elevated zone is really critical to influencing the convection initiation and the growth of the storms on these nocturnal convection events. However, the lessened evaporation and entrainment is, I'm sure it's also a key parameter in allowing or in enhancing the forecast skill using these MPD profiles.
Thanks, Jørgen, for that question. We have a question from George Bryan. What is the nominal temporal resolution of MPD data? Can you see boundary layer rolls? And do you need to temporally average the data before assimilating MPD data in a DA system?
Yeah, that's a good point, George. The temporal resolution of MPD, I believe we can get profiles every 1 minute. However, it's super noisy, and there's not a really strong signal when we look at data with that temporal frequency. I haven't seen boundary layer roll with the MPD data set, but I think that it would be possible. I just haven't haven't identified the perfect data set of rolls propagating over an MPD site to really investigate that question. And yes, we definitely average the data before assimilating MPD into the DA system. For the first experiment that I showed you, the real data assimilation OSE from the MPD network demonstration project, we averaged the MPD data for 15 minutes before assimilating it.
Great. Thanks, George. Thanks, Tammy. We have a question from Matthias Steiner. What is the just beyond the horizon capability that you wish you could get ready for your next field experiment, and why?
That's fun to think about, Matthias. I would really like to see the combined temperature and water vapor profiling MPDs deployed in a network, similar to what we did for the MPD network demonstration project, where we just had the water vapor profiling capabilities. I think that it would just be so exciting to have the combination of the temperature and water vapor. to really assess the stability of the atmosphere. But that's not all. We also need the complementary instrumentation to really depict what's going on in the atmosphere. So MPD alone is not going to answer all of our questions. We need to have the radar scans to know what the pre-convective structures look like, and to identify where the convection initiation and evolution is occurring. We need to know the surface station measurements to categorize or to characterize the fluxes and the surface layer moisture variability and temperature variability that's also impacting the convective development. We need to know the wind profiles. We can obtain this from Doppler Lidars or from wind profilers, and that's really critical in assessing how the convection is going to form and develop and grow. So we need all of the components of the atmosphere to be sampled, and there isn't just one instrument that's going to give us everything. So ideally, we really want these coordinated observational data sets of these multiple instrumentation packages to really best understand these convection initiation and evolution processes.
Thanks, Matthias. I guess this is where Lotus will, I guess that is the strength of Lotus, right? It's that synergy of the surface instrumentation with the radar instrumentation and the profiling instrumentation. That's kind of a grand wish list. So stay tuned for Lotus, right?
Right. Yeah, exactly. Good point, Jackie.
We have a question from Peter Sullivan. Can you get moisture variance?
Hi, Peter. Yes, wouldn't that be great? We just don't have we have high temporal resolution data, but it's so noisy. We just don't have enough power to really get a strong signal to noise ratio back with our high temporal resolution data. So we have to average over long time periods, 5 minutes, where the profiles that I primarily showed you. So with this MPD instrument, it doesn't seem like that's possible. But if you want to investigate that with us, that'd be awesome.
And we have a collaboration. Thank you, Peter. We have a question from Ned Patton. Can you comment on how you selected the 15-minute cycling frequency for the OSE experiments and why? How does this frequency relate to MPD's characteristics, capabilities, or to the turnover time of the most energetic boundary layer structures at the time?
Right, yeah, that's a good question, Ned. This came primarily because these were our first OSE experiments, and we used the expert advice of Glenn Romine, who suggested that we start with 15-minute cycling. So we have 5-minute data available, but it was recommended that really was overkill, and the model probably wouldn't be able to handle that high resolution, high temporal resolution data. We also filtered substantially in the vertical to reduce some of the really reduce the data set that we were using for data assimilation. So these decisions were primarily based upon the best advice from our data assimilation partners at the time. So these are certainly questions that we can further address by doing sensitivity studies on different cycling frequency and seeing if we get any improvement or degradation of the forecast with different averaging times.
Let's add that to your wish list, right, Tammy? We have a question from Chris Burkhardt. Over time, the tendency in modeling has been to run on finer and finer grids. Does this mean that the optimal spacing of MPDs for model assimilation might also get smaller over time?
Yeah, that's interesting, Chris. I'm interpreting your question to mean the optimal spacing of the MPD sites themselves. So, so we can investigate that through the OSSE study, where we're looking at different spacings of MPDs. So first, for now, we've only looked at those different spacings for this one MCS case study. But if we look at different atmospheric features with different spatial scales, I think that we'll get different answers to what the optimal spacing of MPDs would be. As to running it in higher resolution models, we haven't really thought about doing that. We're focusing more on what the MPDs can do for improving our mesoscale convective weather forecast skill. That's something to think about in the future, for sure.
Thanks, Chris. Thanks, Tammy. We have a question from RSF's Vivek. Is there any basis in water vapor measurements? How stable is the calibration of MPD? Bias, I'm sorry.
Yeah,
is there bias in water vapor measurements?
Right. Thanks, Vivek. Nice to hear from you. So we didn't identify any bias in the water vapor measurements when we did our intercomparison study with other multiple water vapor instrumentation. So that included comparisons with radiosondes, comparisons with co-located ARI, comparison with profiling radiometer, and comparison with GPS receiver integrated precipitable water. We did not see any clear bias in the water vapor measurements. And it's a very, very stable. Once we tune the water vapor, once we tune the signal, the online and offline signals at the beginning of the project, it just stays there. And the engineers have also recently made further improvements to the stability of the instrument. So we're really happy with the stability of and the capabilities after the instrument is set up and well tuned. So very stable measurements.
Great, thanks, Vivek. We have a question from Bill Mahoney. What influence radius was used for the MPD data prior to assimilation? Did you study how various distances impact the forecast skill?
Yeah, so the radius of influence used was on the order of 300 kilometers. And this was a parameter within the data assimilation experiment that can be tuned. We haven't investigated a variety of those radius localization parameters. That's something that we can certainly do. And yeah, so we haven't yet gone through the complete tuning of all of those localization fields for our data assimilation experiments yet.
Great, thanks, Bill. We have a question from Jeff Stipp. Very nice presentation. Can you comment on future community field campaigns planned for this capability?
Yeah, hi, Jeff. So that's a good question. We are getting lots of inquiries about MPD availability. It's not yet a deployment pool instrument. We're hoping that NSF will eventually put these systems into the deployment pool. Another path into the deployment pool might be through Lotus. So the inquiries have been for convective weather field campaigns, boundary layer studies. So that's what the community is asking about so far. And I think that it might be due to information exchange, that those are the communities that are most aware of the MPD becoming available. So those are why we're getting these requests from those boundary layer and mesoscale weather communities. But I could see applications for air quality studies and climate high impact weather studies. So I think that the future is really bright for lots of potential science applications using these MPD systems.
Thank you, Jeff. And Vivek has the final comment that is echoed by myself in thanking you, Tammy. We are past the hour of our seminar. Great questions. Thank you, everyone. If you are interested in this topic and have further questions, please reach out to Dr. Weckwerth via her email, which is provided on the seminar flyer. On behalf of EOL, I would like to thank Dr. Tammy Weckwerth on her excellent presentation on water vapor profiling capabilities of the MPD. Thank you, everyone, and have a great day.
Thank you.